the video notes for volume 1, which I am referring to as disks along the horizontal. And this is example 3 and example 4. But before we do example 3 and example 4, we are going to give you the general formula here. Again, we're taking an area, this area right up here. We're rotating it around the x-axis, which is going to give us a volume, and the way we find the area of that volume is by taking a series of disks. Let's see if I can do this. That's not a disk. Try again. That's better. That looks more like a disk. So we have a disk. Do we have a disk? Yes, we have a disk. Slightly off kilter disk, but we have a disk. So we're taking this disk, we're figuring out the volume of this disk, and then for every x between A and B, we find the volume of those disks and add them all up together. So we then end up with, as our general formula, we are taking the integral from A to B of all of these disks. The volume of a disk is pi r squared. The r is f of x, squaring that, and then to get the volume we multiply by the width, which is dx. So that's our general formula. Or, since pi is a constant, we can take the pi and write it on the outside of the integral symbol, and we get pi times the integral from a to b of f of x squared dx. Alright, so an example here. So we're taking the area bound by y equals x squared. So here is the x squared minus 4x plus 5 from 1 down here out to 4 here. And when we rotate this around the x-axis, we get a shape that looks sort of like this, kind of like a bugle, if you will. The integral that we use to find this volume, we are going to take the integral from 1 to 4 of pi. I'm going to put the pi on the outside of the integral symbol. The function, which is telling us the radius at any given x. So this here is the radius. So we're going to do pi r squared. So we're going to take and square the radius, and we multiply that by dx. Now, to do this by hand, you would need to square this out. You would end up with all of those terms, and then you find the antiderivative of each of the terms. It would be long and a tad bit tedious. Fortunately, you have a calculator, so you take this piece here, the f of x squared, and you put that into your calculator. You put that in as y1, and then once you have that in your calculator, you can simply find the integral of that, which would be second calc, and then the seventh option, which is the integral of f of x, and you do lower bound of 1, upper bound of 4, and you should find that that is equal to, oops, let me do this again. Doing this right now on my calculator as we speak from 1 to 4. It's 15.6. 15.6, and then that's going to be times pi. Okay. Last example. Example 4. We're going to consider the area bound by these two functions, y equals the square root of x and y equals negative x plus 6. I have here those two functions graphed. Right, so here is the y equals the square root of x, and here is y equals 6 minus x. And the area that we are interested in is this area in here. And we're going to take this area all in here, and we're going to rotate it around the x-axis. Now, in doing that, the radius for any one of those disks is going to go from the x-axis up to the function, from the x-axis up to the function, or the other way to say that is from the function down to the x-axis. It's just the height, the y value of the function. Now what happens is right here, which we can see from the graph is at the point 4, 2. If you didn't have a precise graph of this, 4, 2, you could simply take this function, set it equal to that function, solve, you'd end up getting a quadratic, and the two intercepts for that quadratic are y equals 2 and y equals negative 3, and we're looking for the y equals 2 intercept. Now the thing about this is we're going to need to do our integral in two pieces, because we have the first set of disks which are when we spin this shape around the x-axis, and then we have the second set of disks, which is when we spin this shape around the x-axis. So the first integral, let's see, we'll make this a little smaller, give ourselves a little bit of room to do this. The first integral we'll put down here, we'll put it down in red, and we are taking the integral from 0 out to 4 of, put the pi here, pi r squared, which is square root of x squared dx. And then the second integral is going to go from 4 out to 6, and this is 6 minus x squared dx. And then we'll do these out. So the first one, this is going to be pi, and we're going to end up with, let's see, so this is going to be x, the antiderivative of x is going to be x squared, so this will be 1/2 x squared from 0 to 4, and then plus the second integral, which is going to be pi times, we're going to need to square this out, so let me do that over here. So 6 minus x, the quantity squared, is going to be 36 minus 12x plus x squared. So then we're going to want to take the antiderivative of this, and the antiderivative of that will be 36x minus 6x squared plus 1/3 x to the third, and we're evaluating this from 4 out to 6. And then we'll evaluate this, and we'll evaluate the second part. So here I have evaluated the first integral at the upper bound minus the first integral at the lower bound, the second integral at the upper bound, the second integral at the lower bound, so upper bound minus lower bound. And while doing that, I noticed that, and I'm curious as to how many people also noticed that right up in here, I am missing the pi. Right? So it should be pi right there, because we're doing pi r squared. So now I will continue this, which gets us to here, pi times 8 plus pi times, oh, what is that? 2 2/3, which gives us a final answer of 10 2/3 pi as the volume of the solid here that's rotated around the x-axis. And we're done with the last part of these notes.